So in the last class, we were discussing, the a part of our enzymes topic. So this slide I have already explained, and then we went through this. Then we saw this, that enzymes reduce the activation energy and they have multiple intermediate steps. Then we also saw the reaction intermediates, rate limiting step, and the activation energy barriers being crucial for life. So up to this we discussed in the last class. So we'll continue from here. So enzymes are extraordinary catalysts. It's not like a little help. Like you put a spoon into a tumbler, having sugar in your tea and mixing it, and without that spoon, if you just shake with the hand, also it will get dissolved, and that help by the spoon is not that great. It is some catalyst, but not great catalyst. But enzymes are not like that. They accelerate the rate of the reaction like several orders of magnitude as listed in this table. So if you take the last one, this orotidine monophosphate decarboxylase, it accelerates 10 power 17 times that of the uncatalyzed reaction. So this is typical, 10 power 5 is kind of on the lower ones. Most enzymes are in this order, like 7 to 11 orders of magnitude. They accelerate the rate of the reactions. So they are extraordinary catalysts. And they are very specific. This I have highlighted multiple times. An enzyme that will phosphorylate glucose at 6th position will not do so for galactose at the 6th position. And I think the last time I used the example of digestion of starch versus cellulose. The enzyme in our body will hydrolyze starch into glucose, but not cellulose into glucose. So enzymes are very specific. So two important points here shown in these two bullets. One, they are extraordinary catalysts and they are very specific. Both of these features are accomplished using very similar similar mechanisms. So they achieve these two by these two features listed here. One, rearrangement of covalent bonds in the reacting molecules. And second, several non-covalent interactions between enzyme and substrate. When the substrate binds to the enzyme, multiple non-covalent interactions, hydrophobic interactions among hydrophobic groups, for example, leucine, isoleucine, or aromatic amino acids like phenylalanine, tryptophan, and so on. And you have polar groups available, hydrogen bond forming possibilities. You have NH2 group and then you have OH. So you have multiple electronegative atoms with the hydrogen bonded to them, and as a result hydrogen bonding possibilities. So you could have a covalent interaction as well among like groups like serines hydroxyl group, threonine hydroxyl group, cysteines thiol group, and so on. So these interactions, many of them are non-covalent, and therefore individually the strength of such interactions are a very low, but then they are in large numbers, so they all add up. So these non-covalent interactions between enzyme and substrate is really the key point when you talk about enzyme catalyzed reactions. And why am I elaborating on this non-covalent interactions is because they are primarily responsible for fulfilling these two, that is extraordinary catalytic power as well as the specificity. So if there are going to be a lot of such interactions, then specificity is going to increase. The right groups have to be at the right place, and otherwise the interaction is not going to happen. And the very same interactions that are responsible for specificity, the energy provided by those bindings, those bond formations, all of them individually low, but collectively they add up, and that binding energy helps in reducing the activation energy and increasing the catalytic power. Okay, so both of this is achieved by the same feature of the enzyme, that is multiple non-covalent interactions between enzyme and substrate. And rearrangement of covalent bonds also happen, and that we will see with specific examples as we go along. So the energy derived from enzyme substrate interaction is what we call as binding energy. And this binding energy is a major source of free energy used by enzymes to lower activation energy. So this is something you need to remember. This is characteristic of all enzymes. So the covalent bond formations are specific to certain enzymes and certain substrates. That's not going to be there in every enzyme. Whereas this non-covalent interactions, multiple of them, is common to all enzymes, and therefore their contribution to reducing the activation energy is something that you need to remember as the primary hallmark of an enzyme. And these interactions are optimized in the transition state. So this is something we need to specifically think about. So the substrate binding to the enzyme is not like the way key fits into the lock. So here, the substrate at the ground state fitting into the active site would be same as key fitting in a lock. Okay, the key outside or key inside, it is the same. It hasn't undergone any change in its structure. Whereas when the substrate binds to the enzyme active site, to fit into the active site, multiple groups are specifically oriented in the substrate such that some of the bonds are even distorted. And those specific distortions happening in the substrate that helps in fitting in the enzyme leads to the transition state of the substrate. So now the substrate is at a level where it can actually become product. So this transition state is what is the enzyme's active site is actually complementary to this transition state. So this is an important concept. And similarly, interactions with the substrate leads to reorientation or rearrangement of groups in the enzyme active site as well, which is called the induced fit. The substrate binding actually makes the enzyme also undergo certain conformational change such that the active site is now catalytically a lot more powerful than the one before the substrate bound. So by the time these two bind, already they have undergone changes such that they are catalytically poised for the reaction. Okay, these are very important things to remember about enzymes. So this in a cartoon way it is depicted here. Suppose let us say you have a long metal stick and you want to break. So if you want to go from here to here, this intermediate step is readily understandable. This is how you would have held both ends and given pressure in the middle such that it bends, and the bend form can easily break into two. Without this intermediate step, you don't imagine this breaking like this, unless otherwise you are using a knife-like thing to cut it. And if this is the transition state for this substrate becoming this product, then if you have a device that fits in this manner, it is not going to break into this. So the activation energy barrier will remain really high. But on the other hand, in the process of this fitting into this device, if the device is shaped like this and to fit, it is going to bend like this. This is what we call as a transition state. So the enzyme active site, the active form of active site, is complementary to the transition state and not to the substrate. This is something very, very important and you have to remember. And this process is what reduces the activation energy. And here you are making an important assumption, that is there is an enzyme substrate complex forming. So today for the rest of the class, I'll keep on reiterating this idea of ES, enzyme substrate complex formation. And this is critical to explain the enzyme kinetics, the measurement of the rate of the reaction catalyzed by enzyme, and how that rate gets altered when we change experimental parameters. And those observed effects on the kinetics can only be explained by assuming the formation of an ES, enzyme substrate complex. And so this cartoon very clearly illustrates why enzyme active site is complementary to the transition state of the substrate and not to the substrate itself. So this I have already explained, in the bullets, like binding energy greatly contributes to the reducing activation energy, and as well as the requirement of so many multiple bond formations ensures specificity as well. Okay, so both extraordinary catalysis and extraordinary specificity comes from several non-covalent interactions between the enzyme and substrate, and those interactions lead to transition substrate reaching into the transition state, as well as enzyme active site undergoing conformational changes such that it fits the transition state. And that process of enzyme's active site change is what we call as induced fit. The fit is induced here by binding of the substrate. Okay, so this simple organic chemical reaction illustrates how these things help. So for example, if you take this, you have an ester bond getting hydrolyzed, and then you have an anhydride bond formation. Okay, so this is acetic acid forming an anhydride bond with another acetic acid. So here you have two reactants, and to use our terminology, two substrates. So therefore it is a second order kinetics, where the rate is dependent on the concentration as well, as indicated here in this K times moles per second. And if you take this as equal to 1, like the rate of the rate enhancement, if you arbitrarily take it as 1, and when you link these two functional groups that are going to interact to make this molecule in this manner, now the reacting groups are so next to each other that it is an intramolecular reaction because they are connected. And since it's intramolecular reaction happening only within one, it's first order kinetics, and it is not dependent on the concentration. And by virtue of that itself, from this to this, you have at 5 orders of magnitude the catalysis increasing, the rate increases. But even then, as indicated by these pink arrows, you have bond rotations possible in this. So these two groups need not be just rigidly placed next to each other due to these rotations. Now, if you constrain these rotations by adding additional structure to it, and these are rigidly held, then they more readily react, and that is another 3 orders of magnitude reaction increasing. This is the sort of thing that happens in the enzyme active site. The first thing, binding of the two reacting groups in the active site converts from an intermolecular reaction to an intramolecular reaction. Although the reacting groups may be on 2 different molecules, but now in the active site, when they are bound, they are virtually converted into a single molecule, and therefore it's like intramolecular reaction. And then further interactions with the other active site groups in the enzyme probably orients the functional group such that they don't even have this much free flexibility, and due to that the reaction more readily happens. Okay, so this is the entropy reduction. Okay, so here the entropy is very high, reduced, further reduced. And the second one the substrate, all enzymatic biochemical reactions in our cell or in our body, if you are talking only about a human, all happen in an aqueous environment. It's all water based. So the substrates are well, in interaction with water. They are hydrated. So you have a hydration shell around them. So if you have an amino acid, the carboxyl group as well as the amino group, and if the side chain has polar group, they are all happily interacting with water. When they are happily interacting with water, they are not going to interact with someone else. They are not even seeing someone else. So getting the molecule out of water actually is important for the reactions to happen. So the binding at the active site takes the substrate away from water, and that is why it is desolvation as an attribute for rate enhancement. Then these weak interactions thermodynamically compensate for the distortion. Okay, normally in free solution, those distortions are not stable. They are not thermodynamically stable. They are like somebody walking on a rope few hundred feet above the ground. They are going to fall down. But instead, these interactions make sure that that person has a belt and handrail around, and therefore he is not in danger of falling down kind of situation. So these weak interactions make thermodynamically stable those distorted structures. And induced fit is something I have already explained in detail. So these are 4 means by which enzymes actually enhance the rate of reaction. And in addition to this, so here we saw how the enzyme might orient the reacting groups at the functional at the active site. And in addition to this, enzyme active site provides additional groups for specific catalytic mechanisms. 3 of them are listed here. These are the most common ones. So they act as general acid-base catalysis. So here I'll explain this with an example as we move on. So this is one mechanism, and another one is covalent catalysis, another one is metal ion catalysis. So these are the 3 mechanisms that the enzyme active site can actually provide in making sure the reaction happens. So let us look at one by one. So let us take acid-base catalysis. So acid-base catalysis means for a reaction to happen, temporarily if a proton needs to be abstracted and the resulting charge is unstable, if the intermediate with the resulting charge is unstable, and if it is going to readily break down back into substrate, then the reaction is not going to happen. But on the other hand, if someone can hold on to that proton, or someone can balance the charge in the intermediate, then the intermediate will become stable and it could go towards the product. So therefore, proton acceptors and proton donors can actually be very helpful in making sure certain reactions happen, simply because the transition state intermediate is probably an unstable charged structure that normally tends to break down back into the substrate. So they don't cross the barrier. They climb the mountain, but then they constantly slip back. They don't reach the peak to go to the other side. And there, if someone stands on the peak and holds the hand, then this molecule can get there. So there is that sort of an analogy. So since these reactions happen in aqueous phase, water itself can do it. So we have seen that water can ionize into hydronium ion and hydroxyl group. That one water ionizing, the proton gets hydrated, and that is why you have hydronium ion. So water itself can do this. So if the electron transfer, or rather the proton transfer to water is faster than actually breaking down to substrate, then the reaction will happen on its own in water environment. Okay. So in this example, what you are saying is, we're seeing is Without catalysis, the unstable charged intermediate breaks down into the reactants. But on the other hand, if the speed with which this proton can transfer to water, then the reaction can go forward with water acting as the proton acceptor. Okay, I'm ignoring temporarily for simplicity the proton donor part. So I'm only talking about the acceptor part. So water itself will do it. And when water does that, you call that a specific acid-base catalysis because it is specific to water doing the activity. So when proton transfer to I just said this, I just want to read it once more for clarity. When proton transfer to or from water, that is acceptor or donor situation, is faster than the rate of the breakdown, like from here going back. If this is slower than transfer to water, then it readily happens in water itself. You don't need to have any other proton acceptor or donor. Okay, and their presence doesn't help because the rate of transfer to water is faster and water is there plenty. So you're not going to have something that can do better than water. But on the other hand, if the proton transfer to or from water is slower than the rate of breakdown, okay, so that means this happens a lot faster than the water, taking care of this charged intermediate. Then very little gets stabilized in this, or rather in this structure. So they mostly remain like this. Under that circumstance, if you have one more group that can very readily accept proton or donate proton faster than the transfer to water, then that helps in the catalysis. So when they provide a proton, then you call it as acid catalysis. When they accept, then you call base catalysis. Okay, so and this is what you call as general acid base catalysis, where the proton donor or acceptor is not water but something else, and that you call as general acid base catalysis. So here the catalyst, by temporarily accepting a proton or temporarily providing a proton, stabilize an unstable intermediate structure. And that then it can move forward, that the group, if you follow the electron flow as well as the color of the atom, from where the proton comes, then you will understand how the reaction is made possible. Here what you are seeing is an amide bond cleavage, okay, which is common in protein. So if you want to break the peptide bond between two amino acids, then you are actually breaking this bond. Okay, so here this is what we are seeing, and this is one amino acid broken down, and here this is attached to this, and this intermediate steps are balanced because acceptor or a donor helped in stabilizing the intermediate step. And this is readily possible in an enzyme active site because we have amino acids with side chains that can donate or accept protons. So this you have already seen when we were looking at the amino acid structures. We will see that once more here. Like for example, here if you take glutamic acid and aspartic acid, they have a carboxyl group in the side chain. Even when their amino group and carboxyl group are in peptide bonds on either side, the side chain carboxyl group can act as a donor, and the dissociated form can act as an acceptor. This, whether it exists in this form or this form, depends on the pH. So as a result, the enzyme activity is highly dependent on pH. So this is something we have already seen. So lysine and arginine, they have the basic group, this amino group, and that can be protonated or it can in which form it can act as a proton donor or it can act as proton acceptor when it is not protonated. And thiol group of cysteine. And histidine's imidazole group, can act like the way lysine and arginine do. And serine and serine's hydroxyl group, tyrosine, this is hydroxyphenyl group. So this group, so similarly, threonine also has a hydroxyl group, so they can all participate in the acid-base catalysis. This is one of the common mechanisms of enzyme-based catalysis. So acid-base catalysis is not specific to only certain enzymes. Many enzymes use this mechanism. Okay, so the next one is covalent catalysis. So where an enzyme's active site group participates temporarily in a covalent bond with a moiety in the substrate. Here, for example, A, B getting cleaved into A plus B. You can take that amide bond, earlier example itself, where peptide bond is getting cleaved. So two amino acids getting hydrolyzed into individual amino acids A and B. So you can think of that situation. Or you can take, sugar getting cleaved into glucose and fructose. So there are many situations where you have this. After all, we are talking about polymers, right? Like nucleic acids, proteins, carbohydrates, they are all polymers. So this sort of reaction is very common. So in the presence of a covalent catalysis, so in this particular case, a nucleophilic group like this, if it is an amino acid side chain, then that can readily attack this bond and get attached to A. So this intermediate can more readily form than these two forming directly from this. This is equivalent to that metal rod in bend position. And now this hydrolysis readily happens, giving regenerating this active site group back and substrate leaving the active site, the hydrolyzed first part of the substrate. So this sort of a covalent bond formation in the active site is what you call as covalent catalysis. This happens quite often with these kind of enzymes like cysteine, serine, threonine, tyrosine, where this hydroxyl group, this alcohol group, or this thiol group participate in covalent intermediate formation. And when these sort of things happen, the new pathway for the reaction, this is one pathway, this is a new pathway. Instead of going from AB to A plus B, this goes via AX plus B and then A plus X plus B. So this new pathway has lower activation energy because this bond formation requires lot less energy, like this transfer from this covalent bond from B to X requires lot less energy than breaking this outright. And similarly, hydrolysis of this requires less energy. And so this is how this new pathway reduces the activation energy compared to the uncatalyzed reaction. And I just told you this, number of amino acid side chains. Cofactors we have not yet gone into, although we have learned initially at the very beginning of the enzyme discussion that metal ions and vitamins function as cofactors and coenzymes. And when they are tightly bound, we call prosthetic groups. So they can also help in this covalent catalysis. So the last one is metal-ion catalysis. So here metals bound to the enzyme active site participate in catalysis. So they could, through their charge, they could interact strongly in an electrostatic manner with the substrate such that the substrate is specifically oriented for the reaction. And again, by virtue of the charge on them, they could stabilize a charge reaction intermediate. Sometimes these metal ions do a lot better than the amino acid side chain simply because the charge on them is higher. And due to that, they can stabilize the transition state better. And they can participate in oxidation reduction reactions by reversible changes in metal ions oxidation state, because many metal ions exist in multiple oxidation states. We will see one great example when we are going to talk about how in photosynthesis, for example, water is split into hydrogen and oxygen, and that exploits the multiple oxidation states of the manganese ion in that particular enzyme. Many ions have multiple oxidation state. For example, ferrous, ferric, cupric, cuprous. So like that, you have multiple metal ions that have multiple oxidation states. And by reversibly going from one state to the other state, they can help in electron transfers, oxidation and reduction, lose electron and accept electron. So these are the ways by which metal ions help in enzyme catalysis. So we saw these acids, these are all separate mechanisms. It's not that an enzyme that uses acid-base catalysis does not simultaneously use covalent catalysis or does not benefit from the presence of a metal ion. Many enzymes use a combination of these catalytic mechanisms. So shown here is a protease, chymotrypsin, which hydrolyzes a polypeptide chain into amino acids. They cleave at the C terminus of lysine or arginine. And this is an amide bond cleavage. It's very much like the one that we discussed a few slides ago. So in its active site, you have a serines hydroxyl group that participates in covalent catalysis. You see here serines, this alcohol group in linkage with the, it's in an ester linkage with the carboxyl group of this amino acid with R1 group. And just before that step, another amino acid side chain in the active site acts as a base catalysis. Okay, it acts as a proton acceptor temporarily. So, like for example, the proton leaving from this is stabilized by this, and due to that, this becomes a reactive oxygen that more readily reacts with this carbon. This carbonyl carbon is going to have charge imbalance here because this is a strongly electronegative, and this is going to have a partial charge, and due to that, this very readily reacts with this, and intermediate covalent structure forms. So initially, base catalysis followed by a covalent bond formation. So this is an example from chymotrypsin. So the main point here is enzymes often employ a combination of catalytic mechanisms. So we have seen three catalytic mechanisms. One is general acid-base catalysis, where the active site group either donates or accepts a proton, and by doing that, it stabilizes an otherwise unstable intermediate. And the second one we saw is covalent catalysis, where a covalent bond is transferred from substrate temporarily with an active site residue in the enzyme, and that is energetically more favorable than converting that directly into product. And then the third we saw metal ions. So here this is an example where we find the first two being used in the single reaction, but there are some enzymes where all three are also used. So this brings us to the end of a general introduction to the enzyme catalysis. Now we are going to specifically talk about how do we get to the enzyme mechanisms. Okay, like how do I find out what specific groups are involved in a particular reaction, and how it is really bringing about the conversion of the substrate to product. The reaction mechanism, essentially the well detailed electron flow diagram. So that is a very challenging question in enzymology. And in modern times, what we do is we really use multiple techniques to identify the active site residues and their orientation. So for example, we purify and crystallize the enzyme, and using the crystal you determine the three-dimensional structure of the enzyme, such that you know what groups are positioned in what way at the active site, and that helps in understanding mechanism. And we also can mutagenize, meaning in the enzyme we can change different residues by combination of methods we call site-directed mutagenesis. By replacing the different residues and looking at the structure and the rate of the reaction, we can really get to understanding of the reaction mechanism. And the other method, which is historically more ancient and still very powerful, is measuring the rate of the reaction and manipulating the rate by changing experimental parameters. So what kind of manipulation of experimental parameters affect the rate in what way? That sort of a measurement helps in getting at the mechanism. And that is what was readily doable before these sophisticated structural biology techniques came. And this is what we call as enzyme kinetics. Okay. Okay. So I was worried that I missed slides. So this is the first slide here. So the enzyme kinetics means you are measuring the rate of the reaction. Okay. And you manipulate the experimental parameters and see the consequence of such manipulations on the rate of the reaction. Doing as enzyme kinetics. And this has been the bedrock of getting at the enzyme mechanisms for a long time. And it continues to do so. Now, the structural biology and site-directed mutagenesis go hand in hand with rate measurements in finally getting at the enzyme mechanism. Okay, so let us now take small steps in understanding enzyme kinetics. So this is a very introductory course. We are not going to get into the kinetics in great detail. So we will only see the preliminary part to get an idea, but to get a flavor of the, how enzymes function. So the first one is illustrated by this graph. So here you have the rate of the reaction plotted against change in substrate concentration. So as you increase the substrate concentration, the rate of the reaction increases. But this increase, the rate of increase keeps changing. Initially, it is steep increase as the substrate increases. But after a point, it starts to slow down. So the rate of the reaction does not increase anymore. And when you reach the substrate concentration at a certain level, at a certain substrate concentration, the rate no longer increases. It has reached the maximum possible rate, and that we call as Vmax. This graph is intentionally drawn with this actual plot not getting to the Vmax, simply because in practical measurements, you never reach Vmax, but you get very close to it. And that is why this dotted line here showing the Vmax point. So this is a characteristic of enzyme catalyst reaction. And this happens, this plateauing off, this rectangle shaped curve happens purely due to what we call a saturation effect. And this saturation effect results from this formation of enzyme substrate complex. Remember a few minutes ago I was telling this, I'll keep repeating this. Enzyme substrate complex formation is critical in understanding enzyme catalyzed reactions. And this readily forms, and from this breaking down to E plus P, that ES breaking down is slow. And that is why when you reach a concentration of substrate in which the definitive concentration of enzyme that you began with, so in this entire process, enzyme concentration is kept constant. So you will reach a point where all the enzyme is in ES, because this readily happens, but then this breaking down to this happens slow. So therefore this K2 reaction becomes rate limiting. And due to that, you reach a point where there is no free enzyme available anymore to combine with substrate. And that is what we call as the saturation effect. And that is the reason why the graph plateaus off. Okay. So this plateauing off or the saturation effect is a characteristic of enzyme catalyst reaction. This doesn't happen when you put the spoon into the tumbler with the sugar and mix it. Okay. So you don't see this in other chemical catalysts. So this is very characteristic of only enzymes, and that is primarily because of ES formation. So in this sort of a reaction, if we are going to call, let us say, V0, we are looking at initial velocity. So the reason we are looking at initial velocity is as the reaction happens, the substrate concentration changes because it is getting converted into product. And therefore measuring the rate in terms of the substrate concentration at later stages is not readily possible, primarily because ES is not easy to measure, because we do not know what is ES and how to measure its concentration. It is an assumption. We try to understand this is what it happens. But of course, ES complexes can be crystallized now and we can know their structures. But even then, while measuring the reaction as the reaction is happening, measuring ES is not easy. So we try to always focus on the initial stage where the substrate change is very little that it can be actually ignored. And this V0 is what we focus. And the initial velocity V0 will be a function of ES. And since measuring ES is not easy, people had to derive an equation where it can be defined alternatively, where the components of that equation can be readily measured. And that was accomplished by two famous scientists, Michaelis and Menton. They did this work more than 100 years ago. 1913, they put forward their equation. And more than 100 years later, it is still the way we measure the rate of reactions. Okay. So forever you are going to remember Michaelis-Menten equation, regardless of which branch of biology you are going to learn. So essentially what Michaelis-Menten equation does, it relates the reaction rate with substrate concentration. So by measuring the substrate concentration, I can get an idea of the rate of the reaction. So that is the equation they provided us. So let us look at how to get to their equation. So their equation in modern times is very simplified. So we have a simple way of deriving this equation. And we make a couple of major assumptions, and we make ourselves aware of two important facts in the process of the reaction. So the first assumption is that we are measuring the rate of the reaction very early, okay, the initial rate. So we have two stages here. There is one thing called pre-steady state, meaning before reaching the steady state. I'll explain steady state as well. First, the pre-steady state is very initially ES is just forming, ES is just accumulating. That is pre-steady state. Okay, so there was not enough ES and only ES is forming. So even this is not happening, only K1 is valid. And after some time, still very initially in terms of the amount of substrate getting converted into product, you reach steady state, meaning you reach a state where ES concentration remains constant, meaning the ES breaking down either side, like going back to E plus S or E plus P, like K minus 1 or K2. Now K minus 1, K2, these two reactions are equal. The rate of these two reactions are equal. That is what we call as the steady state. That is when ES concentration is going to remain constant. So the first assumption is we are measuring it very early, such that the substrate concentration is very high and the product formed is negligible, and as a result this K minus 2 equation, this reaction we are going to ignore. That is assumption number 1. Assumption number 1 is that we are measuring very early at a point where the concentration of product is negligible. Therefore, we do not consider this reaction, this reverse reaction of E plus P giving ES. And that is the reason K minus 2 is not shown in this equation. It is not because this is an irreversible reaction. Under this condition, the rate of the reaction will be equal to so this is the rate of the reaction, ES becoming E plus P. So that is what will be actually S having become P. So this is the rate limiting step. So that is the one that is going to define the rate of the overall reaction. This we saw at the very beginning. And therefore, it is proportional to the concentration of the reactant. So here that is ES. And that proportionality constant is K2. So V0 equals K2 ES. So this will be the rate of the reaction under this assumption. And we can't readily measure ES, I just told you. And due to this, we need to rearrange this. And that is what Michaelis-Menten did. Michaelis and Menten did. So before going into assumption 2, we are going to remind ourselves of 2 important facts here. One is we are going to call the total concentration of the enzyme as ET. So enzyme can exist as free unbound enzyme or bound enzyme as shown here. So ET will therefore be equal to ES plus E. Okay. So this is unbound enzyme. Or rather, if you want to always talk about the free enzyme, unbound enzyme, then that will be ET minus ES shown here. So this idea of ET we are bringing into our attention here. And the second one is we are assuming that when the ES concentration is very low compared to substrate concentration, remember we are measuring initial rate. This is the major assumption here. So the amount of amount of substrate bound to the enzyme is going to be negligible. So we are going to actually ignore that. In that sense, the K2 will actually be equal to ET. ET meaning the total enzyme. So you need not worry about that point for now, but we just are aware that initially the fraction of the substrate existing in the form of ES will be negligible. Okay, so with those 2 in mind and with that assumption 1 that we are measuring initial rate, we go to the second assumption. So second assumption I kind of mentioned already while defining the pre-steady state. I had to define steady state. So the steady state is what is assumption 2. So we assume the reaction is at steady state where the ES formation and breakdown both are equal. Okay, so this is the major assumption of the Michaelis-Menten kinetics here. So now let us look at the rate of ES formation. Rate of ES formation will be dependent on the concentration of these two, and then we have already defined EA equals ET minus ES, so that's introduced here. Instead of calling K1 equals E times S, we are calling it as ET minus ES times S. And rate of ES breakdown, therefore, is this. One is ES breaking down. So therefore, it is K minus 1 times S plus also K2 times ES. So breaking down in this direction. So if it is steady state, then this equals this, and that is stated here. Then you multiply this and you get this, then you rearrange and simplify, then you get this. So in the interest of time, as well as assuming that these are all very, very simple algebraic equations, and you have done a lot more complex ones in maths. I'm not taking time to derive the equation myself, and instead I am directly showing it in PowerPoint. I hope it is not a problem for you to understand. So now to further simplify, what we are going to do is we are going to add this factor to both sides. And when you do that, and when you do this to this side, then it becomes just K1 ETS. And this side, if you add and then rearrange, then you get this. And when you try to bring all these constants together, and you derive the equation, solve it for ES, like you take this ES out. So it'll be K1 ETS, that's what is this side, and then divided by this. Now you rearrange such that all the constants are together, then you get this equation. Okay. And all these constants together, we call them as Michaelis-Menten constant, or Km, which is an important parameter of enzyme catalyst reactions. Okay. And now our goal, we know that ES cannot be readily measured, so it has to be rate of the reaction. So we are going to go further with it. And since V0 is, just to remind, I have it here, K2 ES. So therefore, now ES is this, that means you multiply this with K2 to get V0, going by this relationship. So V0 equals K2 ETS divided by Km plus. Now we know ET is the maximum enzyme available. So Vmax will directly be dependent on ET. At that point, when the substrate constant is very, very high, you are going to ignore the ES component there. And therefore, K2 ET is what will be Vmax. So you substitute this K2 ET with Vmax, then you get the Michaelis-Menten equation, which is V0 equals Vmax S divided by Km plus S. Okay. So this is the major equation for all enzyme catalyst reaction. So here each of these parameters are readily measured. One. Second, this is consistent with observed experimental results. Even if you look at the theoretical points, you will readily understand from that parabolic curve, the saturation curve, that these relationships are met. So let us try to look, I guess I'm running over time, so I'll stop here with the derivation of the Michaelis-Menten equation. So in the next class, we'll look at the implications and usefulness of Michaelis-Menten equation in actual enzyme catalyst reactions.